All right, so we left off on Tuesday looking at strong acids and strong bases and essentially saying that if I'm a strong acid, okay, a strong acid, then my concentration tells me the concentration of H3O plus, okay, which is really telling us the concentration of hydrogen, which allows us to find our pH and so on and so forth. Okay. Now we do have to take into account the number of hydrogens we're going to get, and this is where I was going to lead off, so that homework problem is pretty good with the base question there. If I have something like H2SO4, which is a strong acid, let's say that is our SA, that is our strong acid, and we do have 1.0 molar. Okay. The concentration of H3O plus is really 2 times 1.0 because it's giving me 2 hydrogens for every 1 H2SO4. So the concentration of H3O plus in this solution is really 2. Because we're really looking at how much hydronium I can make, and I can make twice the amount of hydronium to the H2SO4 because I'm going to have 2 hydrogens there. So we have to take that into account in the homework problem, which I was considering, even though I wrote barium hydroxide down there, was sodium hydroxide in my head when we first started doing the math. If this was, 1 molar barium hydroxide, now this is a strong base. Strong bases tell me what the concentration of OH minus is. I've got to take into account I'm going to get 2 OH minuses. So the concentration of OH minus would actually be 2.0 as 2 times the 1.0 there. Okay? And we'll talk about how strong acids, and we call these polyprotic. This is a diprotic. This is a dihydroxide or dihydroxyl base. How they really break down, because they don't break down as, they do dissociate, but they do it step by step, one hydrogen then the next. Okay, so that's one thing you have to take into account with strong acids and strong bases. Now, what about weak acids and weak bases? Weak acids don't completely dissociate in water, so I can't assume that their concentration, of the acid is the concentration of hydronium. So for a weak acid, a weak acid's concentration does not equal the concentration of H3O plus. For a weak base, the concentration does not equal the concentration of OH minus. We have to take into account the Ka value and something called the Kb value for our weak acids and our weak bases. This is, again, we talked about it at the beginning of the chapter, the dissociation constant for an acid. This is the dissociation constant for a base. Now we write them just like QC and KC and all of that stuff, where it's products raised to their coefficients times or over the reactants raised to their coefficients. But we have to take these into account. So let's say we had a problem, and it said find the pH, the pOH, all of that stuff that we were finding last class. But it was for 1.0 molar acetic acid. Okay, so they said you have 1.0 molar acetic acid. They tell you that the Ka is 1.8 times 10 to the negative fifth for that. And they want to know the pH, the pOH, the concentration of hydronium, and the concentration of hydroxide. All right. Our first step is to write what it would look like if it dissociated in water. So if I dissociated in water, CH3COOH would become CH3COO minus, right? I'm going to write it a little bit smaller here. Plus our H3O plus because it's an acid. So that's the first thing you have to decide. They're giving me a concentration. Is it an acid or a base? Once you decide if it's an acid or a base, is it strong or is it weak? If it's strong, this is telling me the concentration of hydronium, or at least allowing me to get there. If it's weak, we've got to do an extra step. Okay, so here's our equation. Now, I would write the Ka out as my second step. The Ka is going to be the concentration of CH3COO minus times the concentration of H3O plus all over the concentration of my acid CH3COOH. Now I know this is a weak acid because it contains carbon. I can look at the number of hydrogens to oxygens. Okay, however you want to do it. Well, I only know one of these values, 1.8 times 10 to the minus fifth. I know that that's my Ka. I've got to figure out these. And how do I figure out these? Our friend, Icebox. It's back. My initial concentration of the acid, they told us, is 1 molar. I have no CH3COO minus. I have no hydronium. It's a 1-to-1 relationship, so this is going to go down by some value x. This is going to go up by some value x. This is going to go up by some value x. Therefore, I have 1.0 minus x for my equilibrium concentration for the acid. I have x and x for my concentrations of anion and hydronium. So we're just doing icebox like we did last chapter for weak acids. That being said, I could plug in the values. CH3 is x, H3O plus is x. CH3 COOH, acetic acid, okay, is 1.0 minus x. So if I could solve for x, I could find the concentration of hydronium. If I can find the concentration of hydronium, I could find the concentration of hydroxide, the concentration of pOH, the pOH, I should say, and the pH. The thing is, I have to be able to solve this for x, and we're in that issue where I'm going to have x squared and an x, and I'm going to have to use the quadratic. However, the 5% check could be our friend. Since I'm a weak acid, I only partially dissociate. If I don't dissociate more than 5%, then I could scribble that out. And now I'm left with a simple equation that basically says x squared equals 1.8 times 10 to the minus fifth. Now, if we do that math, square root of 1.8 exponent negative 5, take the square root, I get 0.004. I get x equals 0.004, which would be the concentration of hydronium, as long as the 5% check checks out. So before you go and answer these questions up here, make sure the 5% check works. And if you don't remember the 5% check, The 5% check is take your change, which is the 0.004, put it over your initial, which is 1, and multiply by 100. If it's less than 5%, you can make that assumption. This ends up being what? 0.4%? Only breaks down, so it's okay to make this assumption. So, this, and if you want to double check it and really sit there and do the quadratic, solve this, do the quadratic, and you'll find out that the answer is pretty much the same. Trust me, they wouldn't allow you to estimate or delete things or remove things if the math wasn't accurate. So this is our concentration of H3O plus then, because when I go back into our table, X is that. Now that I have this, I could figure out the pH by taking the negative log of this number. I could figure out the pOH by taking 14 minus the pH. I could figure out the OH minus, whether I want to do 10 to the minus pOH or I want to set up Kw. Okay. If the 5% check doesn't work out, you have to go back and use the quadratic formula. On an exam, I'm not going to make you use the quadratic. Everything's going to work out fine. You might have to do the 5% check to make sure. But in a real life setting, it might not work out perfect. You also might run into a professor who doesn't like the 5% check. That makes you use the quadratic. That says it's more accurate, which I ran into. When I teach Gen Chem, I teach the 5% check. This person taught an upper level chem class and didn't like it and didn't even know about the 5% check and said, nope, they'll do the quadratic. I don't want to see this 5% check thing. Even though I explained, like, the numbers are still going to be the same, they wanted to see the quadratic. So I'm not going to say that you're never going to see the quadratic or have to use it for a weak acid or a weak base. So to finish the problem off, let's answer the questions just for completeness. I want to erase this down here. We'll keep the 0.004. And we'll start filling in our answers here. Okay, so the 0.004 is our concentration of hydronium. The pH will be the negative log of that number. 2.37. The pOH will be 14 minus that number, which will be 11.36. Okay. And then 10 to the negative 11.36 should give us the OH minus 4.37 times 10 to the negative 12th. Questions so far? Are we okay? We're good? Are we sure? OH minus you could do two ways, Taylor. You could take 10, since this is the negative log of, you could take 10 to the minus pOH. So 10 to the negative 11.36 will give you this. Or you could set up the Kw formula. Kw equals H3O plus times OH minus. So there's two ways to get this. You can either do Kw, which is always 1.0 times 10 to the minus 14th, equals the concentration of H3O plus times the concentration of OH minus, and plug in the H3O plus. Or you could do 10 to the minus pOH, will give you your OH concentration. Okay. Anything else? So those four you could find using Icebox. Now, Ka and Kb are dissociation constants due to the concentration of hydronium due to the concentration of hydroxide. The Ka for our weak acid here, I'm going to keep with the red and the blue now in this explanation. The Ka that was given is 1.8 times 10 to the minus fifth. That's on tables in the slides. It's on tables in the your book. Now, since we talked about Kw and saying that water itself has hydroxide in it, every acid has some hydroxide in it. So if I have a Ka, I also have a Kb. And since they're based on hydronium and hydroxide, the formula we can use again is Kw equals Ka times Kb. So if I wanted to know the Kb of my weak acid, I could actually figure it out by taking 1.0 times 10 to the negative 14th and dividing it by the 1.8 times 10 to the negative 5th. And I get out 5.56 times 10 to the negative 10. Okay, so every acid has a Ka and a Kb. Every base has a Kb and a Ka. Now, there's one more we can look at. pKa is the negative log of the Ka. pKb, since we see that P again, negative log of Kb. Here's the deal. General chemists measure the strength of an acid by its Ka value. A really high Ka is a strong acid. A low Ka is a weak acid. So you'll see your strong acids, the Kas are ridiculous numbers, while my weak acids are times 10 to the negative something. Organic chemists measure acid strength by pKa. Don't know why, they just do. Well, if a high Ka means I'm a strong acid, a low pKa means the same thing. For a weak acid, a low Ka is a weak acid, but a high pKa is a weak acid. Because remember, take the negative log of a big number, get a small number. Take the negative log of a small number, get a big number. And it's the same thing down here. High Kb, strong base. Low Kb, weak base, which means low pKb, I'm a strong base, and high pKb, I'm a weak base. That being said, let's say we had this problem, okay, and we had to do icebox, but they didn't give me Ka. Instead, they gave me, let me just put it in here, 1.8 exponent negative 5. And let me take the log of that number. And they told me that for this problem, the pKa, okay, so the corresponding pKa to this is 4.74. And they wanted me to solve it. I've got to be able to work between pKa and Ka. So again, 10 to the minus pKa is the Ka. Just like our pH and pOH. 10 to the minus pKb is our Kb. Okay? So if you're asked to find a pKa from a Ka, take the negative log. If you're asked to find the Ka from a pKa or pKb, 10 to the minus pKa. Okay? Questions on that? All right, let's look at another one. 1.0 molar ammonia is placed into water. Okay. The reaction, if I'm a base, which I am, should be a conjugate acid and hydroxide. If they told us that the pKb is 4.74, and they want us to find the following. Ready? They want us to find hydroxide. They want us to find hydronium. They want us to find pH. They want us to find the pOH. They want us to find the Ka. They want us to find the pKa. They want us to find the Kb. They want us to find all that information, and all they gave us was this and this. So first thing is, I know it's a base, write out the balanced equation. If you don't write it out as a base, you're going to get the right numbers, but they're going to be for the wrong values. Okay? So, it's a base. It's not an acid. Nitrogen, that's ammonia up here. It's a weak base. So, in order to do this problem, I must have to do icebox. My initial concentration of ammonia is 1.0 molar. I have no ammonium. I have no hydroxide to start. My change, this is going to go down by some value x. This is going to go up by some value x. This is going to go up by some value x. At equilibrium, one minus x, x, x. Now, they gave me a pKb. I want to know what my Kb is. I need to know what my Kb is in order to solve for everything else. At least for these up here. Well, 10 to the minus pKb is going to give me my Kb. My Kb just so happens to be 1.8 times 10 to the negative fifth. Should look familiar. That was the Ka for acetic acid, and that's why I'm doing this one. Now, I want to know the pKa, I want to know the Ka. I don't need icebox for these down here. I could just use this value and find these. A little down and dirty secret. pKa plus pKb equals 14. Okay. So, 14 minus the 4.74, 9.26 is my Ka, or pKa. And 10 to the minus 9.26 will be my Ka. 5.5 times 10 to the negative 10th. 5.5 times 10 to the negative 10th. The question is, what is my OH minus H3O plus pH and pOH? So we come over here and we write our Kb out. Our Kb is going to be the concentration of hydroxide times the concentration of ammonium all over the concentration of ammonia to start. Okay, it was our starting product. So now we fill in what we know. We know that this is 1.8 times 10 to the minus fifth. We know that this is x. We know that this is X. I know that this is 1 minus X. I also know that this is a weak base. I'm going to assume that this change is super small. We're going to find out that X is still 0.004 like we've seen on the last one. I know the math is the same, guys, but it means something different this time. We could still do the 5% check over here. The 5% check, just to make sure, 0.004 over 1 times 100. We're going to be okay with this assumption because, again, it's going to be 0.4%. I know the numbers look the same. In acetic acid, and this is why I chose ammonia and acetic acid, because I knew their Kb values were the same. In acetic acid, when I solved for X, I solved for hydronium. But now, since I'm a base, this X tells me I'm hydroxide. Which means now if and I don't remember what I had as my last answer, but I will go into my answers and find it. All right. 0.004 log. Boom. 2.4, 2.39. The pOH is 2.40. Okay. This is roughly 11.6. And I get 3.98. Let me just make sure I have that right. 10 exponent. .51 times 10 to the negative 12th. Something like that. So it's important to distinguish whether I'm an acid or a base. You could do the math completely right, but get it for the wrong answers. Questions on this? Questions on finding any of these for an acid or a base? Weak. Ka for this one here. Ka times Kb is equal to Kw. You can do it two ways. Two ways. This way or this way. Okay. Now, anything else on that? Because I want to show you something. I'm not going to ask you on an exam, but I want to show you polyprotic acids. Okay. But I want to make sure you're okay with where we're at right now. Now, I'm not going to hold you responsible for polyprotic acids. But I will hold you responsible for understanding what's happening. So, if I go over here, and we look at sample problem 18.10 out of the book. So it says ascorbic acid, known as vitamin C, is a diprotic acid. Notice that it has two Ka values. It has a Ka1 and a Ka2. The Ka1 is more acidic than Ka2. We should be aware of that. Well, what's really happening here with a polyprotic acid is the following. Okay? And I'll show it to you on the slides, but I'll show it to you on the board first, and then you can look through the slide later. If I have a polyprotic acid, it's a weak acid. Okay? And I have something like this, H2A. All right. Now, here's what really happens. Yes, I create hydronium. Okay? I place it into water. Okay? And I get out HA minus and hydronium. Okay? Just like so. It deprotonates, makes hydronium. And if I wanted to write out the Ka for this, the Ka would be the products over reactants. HA minus times the concentration of hydronium. Okay. All over H2A's concentration. And I would set up an icebox. I'd be given a Ka value or whatever. I'd set up an icebox and go through what we've been going through this whole entire lecture. But here's the thing. This here, this conjugate base of this acid still has a hydrogen that can donate. Even though it has a negative charge and it is more basic than the original acid, it still does have a hydrogen it could donate, and under Bronsted-Lowry conditions, I am also an acid. So it has a negative charge, which makes it a base. So this is kind of amphoteric. So what can happen here is that HA minus, the concentration, and we would figure that out, could actually donate another proton. And have a second Ka value. Call it Ka2 to stay with the slides. And that would be A minus times H3O plus all over HA minus. Okay. So my weak acids donate their protons in steps. What I want to point out, though, is acidic-wise, okay? The Ka1 value is greater than the Ka2, which is greater than the Ka3, ... The more I deprotonate, the less acidic I become. So the math on it seems a little complicated, but it's not if you stay organized. So I set up, there's my minion from my other job popping up. Here we go. So let's take a look. Write out our Ka values, which we did. Set up an icebox for our initial protonation. Okay? And we do. We set up an icebox, we get our values, and we set it equal to the first Ka value, and we solve for x. And we find that x is 7.1 times 10 to the minus 4th molar, which means that's how much of this I make, and that's how much of this I make. So I make that much anion, I make that much hydronium. Now the key is with a polyprotic, this value starts the next icebox. Because my next dissociation is this up here, and we do the same thing again, but now we set it equal to the second Ka value. Okay? And they show you the same thing here with phosphoric acid. Phosphoric acid has 3 of them. And this percent dissociation up here, don't get all like freaked out by another formula. This is your 5% check. How much changed? How much dissociate? What was my initial times 100? So 1 molar acetic acid breaks down less than 1%. We got it at 0.4%. 1 molar ammonia breaks down, all right, or does its thing in water, creating hydroxide, all right, only 0.1%. So it only donates, 0.4%. It only donates a very, very small portion on its concentration. Now again, I'm not going to ask you polyprotics on the exam. I do expect that you understand that the more I dissociate, the less acidic I am. But I'm not going to ask it for points on the exam. And say, okay, what is the pH of the first dissociation, pH of the second dissociation? So, you could actually thank Corona for that, because if we were in the classroom and I could see you face to face and do this instead of virtually, we would have probably had it on the exam. So there's one good thing that came out of it, I guess, for you guys. Okay. All right, questions about what we did today? I think your exam is going to be on the 21st. Because I still have one more presentation to do, and I don't want to overload you guys. But I will give you homework on this. All right, so let me go back to the sample problems here and see which ones we can do. All right, 18.7, 18.8. All right. Sample problems. .10 we talked about. Now, where's my base ones? 18.11. .12. in the book. Where are my weak acid ones? Here we go. And how about some bases? Okay. All right, there's the homework.